In this lesson, we will analyze two very fundamental circuits, the voltage and current dividers. We will encounter these two circuits all around when analyzing more complex circuits. Having a good understanding of how these two circuits work will make it easier to understand other complex circuits. In the following circuit, we can see two resistors connected in series. These receive a voltage from a voltage source. In parallel with resistor 2, we have connected a voltmeter in order to measure what's the voltage on this resistor. Voltmeters usually have a very large input resistance, and for that reason, we can make the assumption that practically no current is flowing into it. If that's the case, the current that flows through both resistors is practically the same. Let's try to calculate what's the voltage of resistor 2. In order to do that, first we need to calculate what's the current I that flows through both resistors. And for that, we need to calculate what's the equivalent resistance. If you remember the last lesson, we can do that by adding the individual values of the two resistors. That gives us this equivalent resistor. Next, since we know the input voltage, we know the equivalent resistance, we can use Ohm's law in order to calculate the voltage by simply dividing the voltage 1 over the equivalent resistor. And if we want to know only the voltage of resistor 2, we can use Ohm's law again and multiply the current that is flowing through the resistor by the resistor value. This leads to the following formula, in which we can see that the voltage of the resistor 2 is R2 divided by R1 plus R2 multiplied by the input voltage. Let's check this numeric example. In this case, both resistors have a value of 1 kilo ohm, and therefore the equivalent resistance is 2 kilo ohms. The input voltage is 10 volts, and this is divided by the 2 kilo ohms, and this gives us 0.005 amperes. Then we can calculate the voltage of the resistor 2, which is 0.005 amperes, times 1 kilo ohm, which returns 5 volts. In this case, since the two resistors are the same, then the voltage of the resistor 2 is going to be half the input voltage. If we use the voltage divider formula since the beginning, it's very easy to calculate. 1000 over 2000 times 10, which will give us the same result, 5 volts. Imagine that we have to make the following design using a voltage divider, and this is the specification. There's going to be an input voltage that can go from minus 10 volts to plus 10 volts, and the output voltage must be in the range of 2.5 volts to minus 2.5 volts. Here we have the formulas of the voltage divider, and we can rewrite it in this way. We have that the output voltage is going to be K, which is a gain, times the input voltage, and we can separate this term K and write it as follows. For this example, we need that the term K is equals to 1/4, because that's the number that multiplied by 10 volts gives us 2.5 volts. That leads us to the following equation that we can use to obtain the resistor values. Let's pick some arbitrary values that satisfy this equation, and I will use a resistor 2 equals to 1 ohm and resistor 1 to 3 ohms. As we can see, these two resistor values satisfy the equation. And that's it. We have designed our first circuit. But there is a problem here. Let's calculate the power consumption. For that, we're going to first calculate the current. Using Ohm's law, we know that is the voltage over the resistance, and we have 10 volts as maximum voltage over 1 plus 3. That gives us 2.5 amperes. That's a quite high current. And using the formula for the power, we can see that it leads to a power consumption of 25 watts, which is quite high. The most common resistors are rated for 1/4 of watt, and that will break them. So selecting very small values of resistors can lead to very high power consumption. With small resistors, we have a very large power consumption. Now let's go into the other direction. Let's pick resistors that are very large. In this case, I'm going to select 1 mega ohm and 3 mega ohms. And these two resistors still satisfy this equation. If we perform the power calculation, we can see that we obtain 250 nanoamps, which is very low, and the power is 250 nanowatts. So very large resistors will result in low power consumption, but there are other problems with large resistors. One of them is that large resistors tend to be noisy, and also in this specific case of the voltage divider, they can be problematic. We are going to see an example of that. Here we have two variations of the same circuit, the voltage divider. One of them, it uses resistors of 3K and 1K. The other one, 3 mega ohms and 1 mega ohm. If you remember, in the beginning of this lesson, we mentioned that the voltmeter has a high impedance. In this case, it is represented by a resistor of 1 mega ohm here, and also 1 mega ohm on this side. And here we can see the simulation results. The blue one is from the circuit in the left, the one with 3 and 1 kilo ohm resistors, and we can see that the value is 2.49 volts, which is very close to the 2.5 volts that we designed it for. The reason why it is not exactly 2.5 is because these two resistors are connected in parallel. Therefore, the equivalent resistor value is a little bit below 1 kilo ohm. It is not much because this one is quite large, so that means that there is a little bit of current flowing into this direction. On the circuit in the right, we can see that the results are completely off. We have 1.42 volts instead of 2.5. The reason is that in this case, these two resistors, which are 1 mega ohm, are connected in parallel, and that makes half a mega ohm resistor. Therefore, the formula, it is not correct. So there is a lot of current flowing through here, but also through here. In order to have a better idea on what will be good values for resistor 1 and resistor 2, we're going to try to obtain the formulas for this complete circuit considering the resistor 3. To do that, we're going to follow these steps. First, we need to calculate what's the equivalent resistance of this complete circuit. R2 and R3 are connected in parallel, and these two are in series with R1. That results in the following formula. Then we need to get what's the current that is flowing into this equivalent resistor. In order to do that, we use Ohm's law, and we know that the current is equal to the voltage divided by the resistor, and we have replaced here the value of the equivalent resistor. Then we're going to get the voltage of resistor R1. Using again Ohm's law, we know that the voltage is equal to the current multiplied by the resistor value, and I have replaced here the value of current that we obtained in the previous step. The next step will be to calculate the voltage of resistor 2. For that, we are going to take the input voltage and subtract the voltage of the resistor 1 in order to solve for this voltage. And this is the result. As you can see, this formula considers all the three resistors in order to get the voltage at this point. Just to corroborate this formula, we will calculate the limit when the resistor 3 is infinity. So it will be the value that we will get if this resistor is very, very large. And this is the result. And we can see that this formula corresponds to the formula that we have already obtained for the voltage divider. Let's run a few simulations in order to get a better idea on what values we have to select and also on the impact of the value of the resistor 3. Here you can see the results for the current values. The resistor 1 is 3 ohms, resistor 2 is 1 ohm, and resistor 3 is 10 mega ohms. If you remember the values that we calculated before, we determined that this consumes 25 watts. We can see that the output value is 2.5 volts, which is what we were expecting. If we increase a little bit the value of the resistors, now it's 30 ohms and 10 ohms, the power consumption decreases and the output voltage is still very good, 2.5 volts or very close to it. Let's increase it a little bit more. At this point we can see that the voltage is not exactly 2.5 volts, but a little bit lower, and also the power consumption has decreased and now is 1/4 of watt, so this resistor will be working close to the limit. Let's keep increasing it, and we can see that the output voltage is decreasing a little bit more, but we are decreasing as well the power consumption. If we keep going on, let's see what happens. At this point we have resistors of 3 mega ohms and 1 mega ohms, Since resistor 3 is still large, is 10 mega ohms, the value of the voltage is 2.32 volts, which is already far from the 2.5 expected. So selecting these values will not be good. Let's go back and let's stay around 30 kilo ohms. If we decrease the value of resistor 3, we will see what's the impact. Now it's 100K, and we can see that the value is already far from the 2.5 volts. In order for this circuit to work fine, the value of the resistor 3 or wherever it is connected here needs to be as large as possible or consume little current. And if we go to the extremes, we get either high power consumption or high inaccuracies. Therefore, the best is to stay around the middle, let's say 3 kilo ohms to 30 kilo ohms. Similar to the voltage divider, there is this circuit called current divider, and we can see it in this diagram. We can see that we have a constant current source which is supplying energy to these two resistors. The current has two branches to flow, through resistor 1 and resistor 2. We want to know how much current will flow into each of these resistors. For that, we need to calculate the voltage at this point where the two resistors are connected. Since we know the input current, we need to calculate the equivalent resistance. These two resistors are in parallel, and we use the formula that we already know. After that, we can get the voltage of the resistors, which we know that is the current multiplied by the equivalent resistor. Once we know the voltage, we can calculate the current that flows through each of these resistors by dividing it by the resistor value. For example, for resistor 2, this is the formula which results in this. We can see that it's very similar to the voltage divider, with the difference that instead of having resistor 2 in the numerator, we have resistor 1. To summarize this lesson, we can use voltage dividers to attenuate voltages, and here is the formula that we can use to calculate the values of the resistors. But we need to be careful because connecting additional components to the voltage divider can affect it. Similarly, we have current dividers that we can use to split the current, and here is the formula to calculate the resistors. In general, selecting the components needs to be done carefully based on the design requirements.